We are going to continue with the kinetics unit. The last time we were together, we started looking at calculating rates of reactions by taking data that is available within a balanced chemical equation and then using stoichiometry to determine the rates of reaction for other things in the equation. Then we started looking at orders of reaction. So we talked about the fact that we can manipulate concentrations within chemical reactions and study how those changes in the chemical reaction impact the rate of the reaction, if at all. And so we looked at first order reactions, we looked at second order reactions, we looked at the fact that you can describe the order of the reaction with respect to each reactant, or you can take the sum of all those exponent powers and you can describe the overall order of reaction. So the example that we're going to look at today is the following. So you've got selenous acid reacting with iodide and some acid, and you get selenium, I3, and water. Experimentally, it was found that the overall reaction order was sixth order. So how did they figure that out? They experimentally manipulated the concentrations of each entity and then studied how that impacted the rate of the reaction and came up with a rate law equation. So the rate law equation that was determined experimentally, and I'll keep stressing that word, was the following. Oops, that's supposed to be an E. So the H2SeO3 is found to be first order. The iodide ion is found to be third order, and the acid proton is found to be second order. Okay? Please note that the coefficients in front have nothing to do with these exponents. So there's no relationship between coefficients and powers or exponents. Okay? There's no correlation. It's just by coincidence that they might line up once in a while. But for the most part, they do not have any sort of relationship. Okay, so it says the overall order of reaction is sixth order because what did we do? We took the sum of all the exponents. So 1 plus 2 plus 3 gives me a total of 6. So this is sixth order overall. But we can describe the order with respect to each reactant. So with respect to H2SeO3, it is first order. With respect to the iodide ions, this is third order. With respect to the protons or the acid, it is second order. Okay. All right. So we've talked about first order, second order, multiple order reactions. We've touched on the fact that the coefficients in the balanced equation have nothing to do with those orders because those orders are calculated experimentally. So the last one we're going to look at is the zero order reaction. So think about this. If I double the concentration of A, in terms of looking at the rate is going to be A to the power of 0, and in math, anything to the power of 0 is 1. So therefore, what we can say is there's no change in the rate. So this is a reaction where you can add as much as you want and you won't see any sort of change in how quickly the reaction goes. So when could you possibly come across a zero order reaction? So think about a reaction where the reaction is taking place on this metal surface. And so if I have molecules that have already saturated the surface, and I can only hold 1, 2, 3, 4, 5, 6, 7 at any given time, until they react and fall off, will there be a space, available. Let's say this one's done reacting, this one will leave, and then another one can come in. And so we can add as many of these circles as we want, but so long as this surface is saturated, the rate will not go up. And so zero order reactions often include some sort of solid phase sometimes, but not necessarily. But this is just an example to show you how a zero order reaction may occur. Okay, so we've looked at orders of reactions. Then the next lesson we'll actually sit there and calculate the orders looking at experimental data. Before we move forward, in this unit, because we're concerned with rates and we're looking at the change in quantities over time, what can we use to determine rates? You could look at the rate at which a gas is produced. So you could have your plunger here at zero volume, and then time how long it takes for 10 ml of gas to be generated. And so you would divide the change in volume over time, and you could determine rate that way. You could also study the rate of the reaction. For example, if you have, let's say, baking soda and acetic acid, and you're producing carbon dioxide gas, you'll notice that there will be a decrease in mass because you're losing one of them into the atmosphere. So what you can do is you can study the change in mass, right, all over the change in time, and that will give you a way of determining a rate of reaction. There are many clock reactions, and we will look at one example in school. But take a look at this. So you can look at a color change and time how long the color change takes. So if I were to change the concentrations of my reactants and time how long each concentration takes to go clear, then I could technically use a visual indicator to determine the rate of the reaction. Another way is to monitor pH. So you could have a reaction in which you could measure the rate at which, for example, the hydrogens are being produced in an acid. You could also measure the rate at which they're being consumed, something like a neutralization reaction. So you can track pH over time. You can also look at conductivity. We do have conductivity apparatus that will give you quantitative values instead of just looking at bulbs. And once again, you can look at that with respect to time and determine rates of reaction that way. So many different ways of measuring reaction rates. Okay, so we have this example where we're reacting magnesium carbonate with hydrochloric acid. This will undergo a double displacement reaction, and we will create magnesium chloride in the aqueous state. Plus, I'm going to make carbonic acid, but remember, carbonic acid automatically decomposes to create carbon dioxide gas and water. So in terms of how we could go about collecting data for this particular reaction, well, if I'm generating a gas, I could measure the time it takes or the volume it takes to generate a specific volume of gas over time, and that would give you a change in change in volume over time as a way of calculating the rate of the reaction. And in this case, you would be looking at the rate at which the product is produced. And remember, the minute you know the rate of one entity in a chemical reaction, then you can easily measure the other or calculate the other rates of reactions. We can also look at the change in mass because magnesium carbonate is a solid. And so in this case, because carbon dioxide will escape, you will have an overall decrease in mass over time. And that you can use to calculate a rate with a change in mass. We can also look at this from the pH perspective. Since we're using hydrochloric acid, you can track the change in pH. So ideally, this reaction will start with a very low pH because it's going to be acidic, and over time that pH will start increasing. So we can look at pH over time. If there was a color change involved, then you could look at color intensity. In this case, there is no color change, but you could also then use the color change as a visual way of determining the rate of reaction. We can definitely look at electrical conductivity. So if we look at our chemical reaction, magnesium carbonate is a solid, and I've got 2 protons plus 2 chlorides. If I write like the ionic equation, I will generate magnesium 2 plus ions plus 2 chloride ions plus water, right? Plus carbon dioxide gas. In terms of overall conductivity, there's more ions on the left than the right, so technically you could look at changes in conductivity over time. We talked about clock reactions, where we're looking at color changes, and we will be conducting the iodine clock reaction in class um, to collect data with respect to clock reactions. You can also use titrations to calculate rates. So what you're doing is you're going to have small amounts of the known liquid being added to the unknown, and you can add small samples and keep that sample, and then um, look at the concentration of reactants at that time when you've added small amounts. And over time, you can calculate a rate, because you can also use a time factor with it. The last one that we're going to look at is quenching reactions. So certain reactions happen really, really quickly, so quickly that you don't have time to measure. So what we can do is we can quench the reaction, which basically means that you can slow it down by adding an excess of a compound that will rapidly react with some of the reactants. So, for example, this reaction is very quickly happens very quickly. Sorry, and so if I want to control this reaction, what I can do is I can quickly add some sodium hydroxide to this. Right? Sorry, I'm trying to add an acid to this. And so what will happen is these two will end up neutralizing and making water, and there won't be hydroxides available for this reaction to continue, and therefore you've quenched or slowed it down. So by adding basically a competing reaction, you can quench it and look at analyzing it from that perspective. So we are not going to do any quenching reactions this year, but just to let you know, those exist as well. So what we're trying to get through in this part is that when you are looking at measuring rates of reactions, and if you are thinking about doing your IA with respect to rates, you have a few options that will allow you to collect data and use that data then to determine the rate of a reaction. And if you're doing an IA, then the rate of the reaction should definitely flow into calculating the order of the reaction and coming up with a nice, suitable rate law equation. So next lesson, we'll look at orders of reactions and calculating them.